Hello, so my name is Pierre Auclair. I'm from Université de Paris in Laboratoire Astroparticle and Cosmology, and I'm currently starting my third and final year of PhD. And I'm going to present you this work that we've been performing with Patrick Peter, Christophe Ringeval, and Daniele on irreducible cosmic production of Relic vortons. So you already had two talks about superconducting strings and vortons, so maybe I can go a bit more quickly on cosmic strings and current carrying strings, while also stressing my motivation for this particular work. So cosmic strings are one-dimensional topological defects, and you expect them to be formed in most symmetry-breaking phase transitions in the early universe. So that can be QCD, electroweak scale, or in what interests me more, grand unification theories at higher energies. And this is something very generic and depends on the topology of the symmetry breaking, and it depends on the property that, as you can see here on the right-hand side, after the symmetry, you have a field that falls into a new vacuum manifold, and if it's not simply connected, you can have a region of space where your field is trapped and forming these one-dimensional topological defects, which have a certain tension and a certain mass per unit length. And these objects have a wide range of observational signatures. In this talk, I'm going to talk about maybe more gravitational signatures like lensing, anisotropies in the CMB, and also gravitational waves. And these cosmic strings, as you've seen in the two previous talks, can also have a current on them that can be bosonic or fermion zero modes, and that can condense on the string and make it conducting and often superconducting. And this current on the string changes a bit the dynamics of the string. And the fact that this current carries an angular momentum means that as your loop evolves and loses energy by various mechanisms, at some point, the angular momentum will prevent the final collapse and stabilize your cosmic strings into a circular object, a stable circular object that we call vortons. And this study, we perform a kind of phenomenological study, but also quantitative study of the dynamical evolution of these cosmic string loops and the eventual accumulation of vortons that can behave like dark matter. So now I have to list the assumptions that we made on the current carrying strings. And in this work, we do not assume that the current carrier is bosonic or fermionic. We just assume that you have a cosmic string network that appeared early in the universe. And at a later time, that we call time of the current here, you have a current that appears on the cosmic string network. And the parameters of our model are the Compton wavelength lambda of the current carrier, either your bosonic or fermionic field, and mu is the mass per unit length of the string that characterizes the energy scale of the first phase transition. And we called R in the following plots, basically the ratio between these two energy scales. And now that you have your cosmic strings that have a current condensed on them, these current carrying loops are characterized by two classically conserved integral quantum numbers n and z that are randomly distributed on these cosmic string loops. And these numbers are related to the charge of the cosmic strings. And when I say it's classically conserved, what I mean is that it's conserved if you neglect quantum effects, and if your loop has a size which is similar, for instance, to the Compton wavelength, then you expect it to decay by quantum tunneling. So you have to, they are only classically conserved. And in this paper, we focus on nearly chiral vortons for which these two quantum numbers are of the cell order of magnitude, which allows us to reduce these two quantum numbers to only one. And in this case, the tension of the string is roughly equal to the mass per unit length. And we have also the ratio between the two energy scale being very large with respect to one. And finally, we also assume that the current sets in very rapidly on the cosmic strings, and that the charge of the cosmic string loop is given via a random process, random walk on the string, thermal process, and is given by this central limit theorem that basically says that the charge on the string is proportional to the square root of its length at formation. So we've seen in the previous talk that for instance, if you have primordial magnetic field, this can source the current on your different strings. But in this study, we don't have primordial magnetic field, and the charge is conserved throughout the evolution of the string. Now, focusing more on loops and vortons, here are the assumptions that we make. So assume you have a loop of a certain length, and it will decay eventually. And in this scenario, at very high energy, after the friction-dominated regime, it will decay by emitting gravitational waves, at least on the very large scales. So in this study, we do energy budget of the string, as the length is proportional basically to its mass. Losing energy means that it loses length. And here we parameterize it via this unknown function called J. So on the very large scales, we assume that the cosmic string network behaves according to the Namu-Goto action, and that your loop emits gravitational waves, and that roughly corresponds to J being equal to 1 on large scales. And this is why here we have this prefactor, gamma G mu, which is exactly the efficiency with which a loop emits gravitational waves. Now, on small sizes, you reach the vorton size, which is proportional to the charge here. And if this vorton size is larger than the quantum wavelength, that is to say that you prevent quantum tunneling, then your vorton will circularize and stabilize. And in this limit, you want J to be equal to 0. So in the following analysis, we leave this function J unspecified, at least to the very last moment when we want to make estimations. But if you want an example of a function that corresponds to this situation, you can have this function, which is a sigmoid. So a composition of, of a hyperbolic tangent, which in the case where L goes to minus infinity is 0, and in the case L goes to plus infinity is 1. And you have a transition at L0 with a certain width sigma. And the final limit that we take is setting sigma goes to 0, saying that basically the vortons are perfectly stable, and in which case the vorton accumulates around this vorton size. But in this analysis, we take this sigma that goes to 0 limit at the very end and I will show you why at the next slide. So now that we have established a framework for the production and the evolution of these loops and finally these vortons, we study dynamically how these evolve. And we write a continuity equation for the flow of loops in phase space. So here the phase space is time, the length, and the charge. So on the left-hand side, you have basically a term that says that the flow of loops is conserved. And on the right-hand side, you have a source term. And this source term is given by, basically given by the infinite loops chopping off the infinite strings, intersecting each other and producing loops. And this gives you this loop production function. So here in the study, we make a simple assumption that there exists a scaling solution for this loop production function, and that it is given by this Dirac distribution, stating that at a given time, all the loops are produced at the same size. Of course, you can think of more elaborate model, like having a power loop, but in this study, we keep it simple. And we solve that equation analytically for any value of J, and we find a distribution of loops for length n and charge n. And you have to distinguish, when you do that, the loops that come from the initial conditions, that is to say, the loops that were present at the time of condensation and that acquired a current at this moment, and the loops that were produced by the network after the condensation, that we call produced loops. And now, these loops, they have different behaviors depending on their properties. And the first type of loops that we have are what we call Doom loops. These are the loops that have a current which is not large enough to sustain their final collapse. At the very end, this means that the vorton size associated with n is smaller than lambda, the quantum wavelength, and that they will decay by quantum tunneling. So these Doom loops have n which is smaller than r in this language. Then you also have what we call proto-vortons. these are loops that have a current which is high enough to sustain the final collapse, but they have not lost enough energy to reach the photon size. So these loops behave like non-Bogotá strings and emit gravitational waves, for instance, and will eventually become photons at some point. And now we finally have the photons. So these are all the proto-photons which have decayed by gravitational radiation and have eventually reached the photon size. And to study them, we performed this little trick to define them. So you remember that I've said 2 slides before here that I set sigma to be different from 0, to be strictly positive. So that means that, well, this is what is represented here. You have a loop that decays via gravitational radiation that will reach the photon size, and it will still decay a little bit below this photon size. That prevents the accumulation at a singular point and allows to define it properly. And so the photons of a certain charge are defined as all the photons having all the loops having a charge high enough and having a size which is slightly lower than the photon size. And the good thing is when you do that, you basically drop the dependence on your unknown J function, and you make the solution quite universal. And it does not depend on the way you regularize the situation. So now that we have calculated the number of photons in the universe, you can estimate the energy contained in those photons, and that energy scales more or less like matter. So they could act as a dark matter candidate. And to estimate that, we calculate the fraction of energy contained in those stable photons. So we basically say that a photon, its energy is more or less mu times its variant length, L. And we integrate out over all length for the photons. And if this quantity is larger than 0.3, so roughly the dark matter content of the universe, you can basically exclude directly this model. So this is this gray region here that you see. And also, let me also comment on this region on the lower part of the graph. And this is a result that was surprising to us, but I think is important. In this region, you see the different colors and different lines. And these originate from the formation of the cosmic string network at the very beginning, at the first phase transition. And depending on the correlation length on the strings at this time, you don't have the same initial conditions in your problem. And it turns out that the population of photons depends on this initial condition. And you have a wide range of possibilities for this correlation length. You can either say that it's set via a thermal process. This is the Vachaspati-Vilenkin initial conditions, in which you have a dependence here on the mass per unit net mu. And in this case, it draws the line in which is dashed black here. And in this case, you basically exclude all of this region here. So values of G mu down to the minus 30 and with huge separation, with quite a huge separation between the energy scales. You also can say that via causality, the correlation length is roughly the Hubble radius. And in this case, you have this solid line here that draws this gray region, which we call the irreducible production of Relic photons. So this region here does not depend on the initial conditions, and it's something that that is pretty strong. Okay, so now I've reached my conclusion. So in this paper, we propose a phenomenological framework to calculate the number of photons as a function of the string tension and also the current carrier energy scale. And in this study, we assume that the main decay mechanism for loops is by gravitational wave radiation. We estimate the cosmological distribution of photons and estimate their Relic abundance today. And it turns out we expect photons to be massively present today, even if no loops were created at the time of string formation. That is to say, even with very large values for the correlation length at the formation of the network. And this allows us to rule out new domains of this parameter space that were previously allowed. And at the same time, with a bit fine-tuned models, this also provides us with models in which photons are shown to provide a viable and original dark matter candidate. And thank you for listening. And now we can move on to questions.